In this video, we will talk about conservation of mechanical energy. We will begin by introducing two types of mechanical energy and the conditions under which they are conserved. We will also see if conservation of mechanical energy is related to work, and if so, in what way. This is followed by some solved examples at the end, based on the things that we have already discussed. There are two types of mechanical energy. The first one is kinetic energy, whose expression is given by half times the mass times the square of the speed of the moving object. So this mechanical energy is associated with the motion of an object. The second type is the potential energy. Now, it could be gravitational potential energy, in the case of which the expression is given by the mass of the object times the gravitational acceleration times the position of the object in the gravitational field, denoted by this h. The second type of potential energy is the elastic or the spring potential energy, which is given by half times the spring constant of a spring and the amount of stretch or compression of that spring squared. And as you can see from these equations, potential energy is the type of mechanical energy that is associated with position of an object in a system. Let's do a quick review on the things that we have seen in our previous videos. The first thing is this so-called work-kinetic energy theorem. Now, it is given by the following, which states work equals the change in kinetic energy. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Now, we are reviewing this because it plays an important role in conservation of mechanical energy. The next thing is to see or to recall that the definition of work in terms of variable force. It's given by an integral of the force function with respect to the coordinate or space. So that is the equation for work for a variable force, a force that varies with position. An important thing to note is that this work-kinetic energy theorem is not a special case theorem. It is a theorem that is true in general. One other thing that we want to review is the conservative force. If a force is conservative, one should be able to express that force as the negative derivative of a potential energy function. So this is a mathematical condition for a conservative force. Examples of conservative forces are gravitational force and spring force, to name a few. Now, let's say you have an object that is being acted upon by a variable force, Fx, and at location, let's say xi, of course the force has the value of Fxi, and as the object moves all the way to, let's say, a coordinate xf, the force there is Fx, evaluated at xf. So in this system, you have an object being acted upon by a conservative force. So we say that this is a conservative system. Let's first try to calculate the work done by this force F as the object moves from xi to xf. Now, work is given by F x dx. In this case, the coordinate changes from xi to xf. But we also know from this equation that the integral of fx dx, namely work, equals minus d dx ux dx, which is minus integral of dux. So now for an object that moves from coordinate xi to xf, as in this diagram, then the limit for this potential energy integral will be also xi, xf, which is minus uxf minus uxi. So this is the potential energy at the final location, potential energy at the initial location, which is none other than the change in potential energy for this object. So the conclusion is, this is the same as that. So we see for conservative system only, the work done is minus the change in potential energy. So this is only for conservative systems, namely systems acted upon by conservative force. So this is only a special case, namely it applies only to conservative systems. Combining with the work-kinetic energy theorem, which says work equals the change in kinetic energy, we end up concluding that the change in kinetic energy equals the minus change in the potential energy. And since the change in kinetic energy is the final kinetic energy minus the initial kinetic energy, and the minus the change in potential energy is initial potential energy minus the final potential energy, now rearranging this expression, we get the final kinetic energy, bring the final potential energy to this side, it becomes the final potential energy equals the initial potential energy, bring the initial kinetic energy to that side, plus initial kinetic energy. So in a system that contains only two types of energy, namely kinetic and potential, K plus U is quite simply the energy of the system. So what this equation is saying is the final energy of the system equals the initial energy of the system. Or more accurately, the final mechanical energy of the system equals the initial mechanical energy of the system. So this is the conservation of mechanical energy. And as you can see, conservation of mechanical energy is true only for conservative systems. So if a system has non-conservative forces like friction, then conservation of mechanical energy will not work. Let's look at the problem associated with conservative force. So certain conservative force given by this expression, calculate the corresponding potential energy function associated with this conservative force given that at x equals to 0, the potential energy is 0 joules. Using the fact that minus the change in potential energy is work, and if we take the change in potential energy between, let's say, 0 and some arbitrary point in x, the left-hand side will simply becomes minus ux minus u evaluated at 0 equals work, which is just the integral of fx dx from 0 to x. Substituting the expression for force in that integral, we will get this, and using the fact that u is 0 at x equals to 0, so this term will go to 0, and we get ux is 0x 70x, because this minus will cancel this minus and that minus, we can make it positive, plus 10x squared dx, which is simply 35x squared plus 10 over 3x power 3. And that is the potential energy function for that conservative force. Let's do a problem on conservation of mechanical energy. A ball is thrown from a roof of a building, 28 meters in height, with an initial velocity of 15 meters per second, directed at an angle of 37 degrees above the horizontal. Now use the energy methods to calculate the speed of the ball just before it strikes the ground. So the situation is depicted in this diagram. Now we want to determine the speed when the ball hits this point. Now remember, when you're using conservation of mechanical energy, you must identify the initial point and the final point. So the final point is, of course, when it hits the ground. The initial point is the roof. So we write the conservation of mechanical energy like this. The initial mechanical energy equals the final mechanical energy. So at this initial point, of course, it's moving with 15 meters per second. So certainly it has some kinetic energy at the initial location. Now we can take the potential energy to be zero at the ground here. So it will have a potential energy there as well. At the final point, it's moving with some speed which we want to determine. So it has some kinetic energy there. But since we have taken the potential energy to be zero at the ground, the final potential energy is zero. So putting in the information, we will get, so in this equation, the initial kinetic energy is given by that, initial potential energy is given by that, and the final kinetic energy is given by that expression. The mass cancels, all the terms have mass in them, and we can solve the final speed, which is 27.8 meters per second. So that is the answer with which the ball strikes the ground, keeping in mind g is 9.81 meters per second squared. So another problem on conservation of mechanical energy. A block of mass 10 kilograms, as shown in the diagram, is released from rest on a frictionless incline at an angle of 35 degrees. So that is from there. So of course the spring constant of this spring is given by 12,500 newtons per meter. So what happens is that this block slides all the way down, and then it will hit the spring and compress the spring up until the final point. So at the final point, it will stop momentarily when the compression of the spring is 5 centimeters. So how far does the block move from the rest position I to the final position F? That means what is D? Using conservation of mechanical energy, EI equals EF. So EI is the potential energy at the initial location plus the kinetic energy at the initial location equals potential energy at the final location, kinetic energy at the final location. Now we know that it is released from rest, so that means Ki is 0. We also know the block stops momentarily at the final location, so Kf is 0. Remember, we have the freedom to set u to be 0 at some point, and I'm going to choose the initial point to be u equals to 0 joule point. So that means ui is 0 as well. Now d is the distance measured, let's say like that. Now we remind you that this u equals to 0 is the gravitational potential energy. So at the final point, there are two different kinds of potential energy. The final spring potential energy and the final gravitational potential energy. The final spring potential energy is half times K, which is 12,500, times the stretch, which is 0.05 meters. So it's 5 centimeters. It's converted into meters. And the gravitational potential energy must be negative because on top is 0. So all the lower levels must have a negative value for UG, which is 10, mass is 10, G, gravitational acceleration, D sine 35 is the vertical distance it is falling through. So this is D, this is 35, so this is D sine 35 degrees. So equating this expression to 0 and solving for D, we get 28 centimeters for D. Block speed as it touches the spring is the speed here before the compression. So that's your final point now. Applying conservation of mechanical energy, we get this line. So as before, this is 0, that is 0. So this is the final kinetic energy and this is the final potential energy. So this term here is this height, it's falling through. And solving for V, we get 1.61 meter per second.